Now we're going to talk about position vectors. A position vector is defined to be one that will start at the origin, which is to say that the initial point will be at the origin. And this is going to be one way that we can represent a vector algebraically. We definitely need a way to algebraically represent a vector because our ability to graph a vector or draw clear pictures is not always going to be as good. So the notation that we're going to use here is these pointy brackets. If we have soft brackets like this, we're talking about an ordered pair on the Cartesian plane. But if we have pointy brackets outside our A and B values, what we're talking about is a position vector that is centered at the origin and terminates at that ordered pair. We would call A and B the components of the vector, and these are real numbers where my vector would terminate if we were a position vector that started at the origin. So let's say this down here again, slightly differently and with a more clear image. So we've got a vector V that is our position vector indicated with pointy brackets, which says that it starts at the origin, and when V is represented with this pointy bracket notation, the terminal point at V of our vector is going to be at the ordered pair. Now AB soft bracket is an ordered pair representing the terminal point, but the vector V is represented with pointy brackets, and that is the directed line segment that has both magnitude and direction. So when we have pointy bracket notation, it means that the terminal point of our vector is going to be at the ordered pair AB, soft brackets on ordered pairs. So let's look at a quick example. We want to find this algebraic notation. We want to find the position vector of our vector V. And what we have is the given initial point, which is 3, -1. So let's go 3, -1 is right here. So this is the initial point of our vector. And the terminal point is 6, 3. So let's look at 6, 3 here as the terminal point of our vector. And our vector is going to start at P1 and end at P2. Now, in order to determine the position vector or the pointy bracket notation for our vector V, we're going to essentially think about what would the ordered pair be that we terminate at if our initial point was moved over to the origin. Well, in that case, what we're going to have to do is figure out how many units did we travel in the direction of X. So in order to get from the initial point to the terminal point, our run was 3 units long, and our rise was 4 units long. So we basically go 3 units to the right and 4 units up, and we land here. And this is the same vector that we are looking at to start with. We've got vector V here, vector V here. It has the same magnitude, the same rise and run, which means that it has the same direction. So it is the same vector. But when I slide it to where the initial point is at the origin, then the terminal point is going to correspond to what we call the components of V, or how far we had to travel in the direction of X and how far we had to travel in the direction of Y to get from the initial point to the terminal point. And those components are what we use to represent that vector V as a position vector. So let's see if we can generalize this to come up with an algebraic method for determining the position vector of any vector, given any initial point x1, y1, and any terminal point x2, y2. Let's figure out what we would need to do to come up with the position vector for that vector. So I'm going to have our origin situated here, and I'm going to arbitrarily choose a couple of points. So we'll say I'm going to stay in the first quadrant just to make things easier to look at. We'll put P1 somewhere in here, and I'm going to go off of the grid and get P2 somewhere up here. Now here's our vector that we're going to call V, and we need to determine the components of V that are going to give us our position vector notation. And in order to determine the components of V, let's consider first of all that this is x1, y1, an arbitrary point, x2, y2, an arbitrary point. If we have to figure out the horizontal distance that we travel, we can determine that the leg of this right triangle, actually let's go ahead and say that we have a vertical distance here too. The leg of this right triangle, the length of that leg right there, is going to be determined by the second x value minus the first x value, right? The second x value gives me the total distance all the way out to here, and the first x value is this negative space distance that I don't want. So I'm going to subtract the first x value from the second x value to get the length of that leg. Slide it up underneath there. Now, in order to get the length of our vertical leg, essentially we're going to take this second y value, which measures all the way down to the x-axis, and then we're going to subtract the first y value, which is just this little distance right here, and we get the length of this leg by saying y2 minus y1. So our horizontal distance to get from point 1 to point 2 is x2 minus x1. Our vertical distance to get from point 1 to point 2 is y2 minus y1. Now I'm going to try to take this. Remember, we can slide vectors around the Cartesian plane. So I'm going to slide all of this stuff down to where the initial point is at the origin now. And we can see then that the terminal point, so let's actually fix this up a little bit. If we've moved it so that the initial point is at the origin, then the terminal point that we land at would actually be now at the x-coordinate, which is x2 minus x1, and the y-coordinate, which would be y2 minus y1. So since we are centered at the origin, or initiating at the origin, this ordered pair with soft brackets become the component of my vector with pointy brackets, right? So pointy bracket means that you're talking about or representing the vector itself, right? And when that vector is located where its initial point is at the origin, the point that we land at become the components of the position vector notation. And those components are determined by the distance, the horizontal distance that we travel, and the vertical distance that we travel in order to get from the first point to the second point. And when I'm calculating these, the phrase that I'm going to be using a lot is terminal minus initial, because we're taking the x value of the terminal point and subtracting the x value of the initial point, the y value of the terminal point, and subtracting the y value of the initial point. So when we use this formula algebraically to determine the position vector, we'll be saying terminal minus initial a lot. So let's go back up to the previous example and see if we can calculate the components of this position vector algebraically. And in order to do that, we're going to say the x value of the terminal point minus the x value of the initial point, comma, y value of the terminal point minus y value of the initial point, right? This is how we calculate this position vector. So our terminal point being 6, 3, I'm going to have x2, which is 6, minus x1, which is the x coordinate of the initial point, comma, y2, which is also 3, minus the y coordinate of the initial point. Let me fix that. Minus -1. And what we see here is that we get 6 minus 3, which is 3, and 3 plus 1, which is 4. So we get the same components and the same position vector calculating this algebraically as we would if we were to draw the vector, slide it to the origin, and determine where it landed on the Cartesian plane.